hour here, we're dealing with phenomena which are happening on very short time scales of a few microseconds. So this is 1 microsecond later, and the height and color of these little spikes are telling you information about the pressure, scaled to the 1.5 megabars that I showed you before, but now associated here with the foil, which is being compressed of palladium and of titanium. Next is another microsecond down, and the next is another microsecond down. And I think you start to see here in the next overhead how this is moving down the little mandrel as this focused energy is being forced onto this situation. Next overhead. We wanted to test our detectors, and so we organized a special experiment in not this instrument, but something completely different, a plasma-focused device. And what you can see here is a neutron rate on the vertical scale going up to a height, I'll draw your attention to, of 20 times 10 to the 15 neutrons per second in a time scale which goes out to a microsecond. These are not unusual results for those experts in the community who have been looking at these sort of things. These are typical results which happen in this kind of an instrument every day. The integrated fluence from here out to the end is 6 times 10 to the 9 neutrons. If I can have the next, we look at the data from the experiment which was conducted the next day, not the 11th, but now the 12th, and the data are plotted here. There are 9,000 data points plotted here every 4 nanoseconds, and of course, as you can see, the screen is pretty well blank. If we expand the scale, however, by a modest factor of 6 times 10 to the 5th, or 600,000, we obtain the results in the next slide. Now, this experiment is a little different than I think any so far presented at this workshop, because here we have a strong time focus, which is when the high pressure is passing through the system, as I showed you in that sequence of slides, and then after the burn is over, the pressure releases and there ain't no more pressure. That takes approximately the time in length of 8.1 millimeters per microsecond to go through the system, and since the system is about so big, the total time for that is something of the order of 14 microseconds. There was an event which looked a little bit big. There is some other things which I think suggest that the counters were working, but this is in this expanded scale of 6 times 10 to the 5th vertical factor. And if we can have the next slide, we focus down on the structure of this particular feature, and I think we arrive at some puzzles. Because of the way the pressure was put into the system, it builds up as I showed you, but after a little while it pretty well goes through the system unaltered. Therefore, one would have expected that if we had produced something, either through any of those metallurgical variables that I showed you earlier on in this presentation, that we would have seen a start, something going along, and then a stop. This particular phenomena bears nothing resemblance to that idea. It seems to be a sharp focus result whose width is at the resolution, perhaps, of these counters and detectors. And so, well, it's a puzzlement. The integral under this, if you press my neutron experts who have helped with this experiment in the audience, is approximately 100 neutrons, but the error bar which we've placed on that is 100 neutrons plus or minus 100 neutrons at the source. Therefore, we conclude whatever mechanisms are possible to enhance fusion rates in deuterated transition metals, they were not present at the detection level and pressures of this experiment. We are claiming here less than 10 to the 4th neutrons, nothing seen, nothing less than 10 to the 4th neutrons, which was our absolute minimal detection limit, and nothing above background in this somewhat different kind of experiment than the kinds of electrolytic results that you've been hearing earlier in this workshop. Thank you very much, Mr. Chairman.
Thank you, Dr. Mueller. Are there any questions for Dr. Mueller? Sherber from Sandia. Fred, can you have an estimate of what the loading of the materials was at the peak?
There was a great many steps which, because of the shortness of the time, I had to not include. These materials were first assembled in the manner that you saw without the high explosive. They were then cleaned by Carol Talcott to remove and flush out, and I think those people know how to do that, any impurities or adsorbed gases or any of the kinds of things we've been hearing. And then they were backloaded at 28 psi, 50 psi to start, and then moving down. The conclusion from that, which Carol told me, was that one could believe that, first of all, what happened in the 72 hours or so that this experiment was waiting for a firing table, that first the palladium deuterated at room temperature to the 0.67 kind of number, which we're quoting as 0.7. Then that caused enough swelling to break through oxides, which were probably on the surface of the titanium foil, and one then saw more loading taking place at that point, so that by comparing the known volume of the structure with the amount of uptake, one arrived at these numbers. After these examinations, we have also done fast neutron detection, as I put in this discussion.
Speak louder.
Very good. We've also, let's pick it up. I am a theorist. After we've loaded these up, you could see from the uptake an interpretation which was such that approximately 0.7 was placed in the titanium. Most of you will recognize that as a low amount, and that's simply the amount of time that uptake was taking in this. You might also notice that we didn't put very much material into this experiment as well. So,
Bill Ayers, electron transfer. Metallic hydrogen and metallic deuterium have been made by cooling and pressurizing liquid hydrogen to above a megabar. Is it possible to do the same thing in your apparatus, to say try to make the metallic hydrogen or deuterium first and then put your shockwave through it?
I think so, but let me defer that question to my colleague sitting in the audience who has sort of indicated that it might not be possible. Possible, but very difficult. The focus here was on trying, as I said at the introductory remarks here, to add hopefully some light to this discussion of possible mechanisms of, which is the focus of this workshop. I'm sorry we didn't see anything. We were prepared to see anything up to from 10 to the 4th neutrons up to 10 to the 11th realistically, but I've given you our conclusion.
Caltech. It seems that the least the theorists can do in this business is to keep the experimenters honest. In your initial overview, you listed 3 parameters that you could twiddle to change the penetration integral. When I learned my quantum mechanics, your parameter big R is given in terms of the other 2 as the classical turning point.
That's correct,
so
as the classical turning points. Here, we were trying for this audience, including our potential television audience, to try and make some detail out of this, which had to do with the canonical thing, which we perhaps both learned in quantum mechanics class, having to do with the height and width of a tunneling barrier. And so it was for that reason that I focused on presenting it that way. You're quite correct in terms of how one might interpret that particular experiment that I alluded to.
Yes. Stan Lockhart, MIT. In the computer simulations of the compression, do you know what the closest approach distance was typically for deuterons in the compression, and what kind of fusion reaction rate would you expect for that approach distance?
Okay, I have some materials which I've brought, which is based on some work of René Leclerc, where these kinds of simple calculations have been done for a number of radii and for a number of screening coefficients. So to just in terms of such a model, make some commentary about the size of potential effects. Normally speaking, one's talking here about potential tunneling on a scale of approximately 10 to the minus 61. One can get better numbers about that. The simulation is a 2-dimensional hydrocode, which is actually looking at this in terms of mesophysics. In other words, there is 10 to the 15 little grid points in there. The Eulerian code follows it through as things are changing their sizes. And then this nice work which Stan Marsh did for 2 hours on the craze That then puts the simulation of pressure in which we've presented here. I might just mention that I think nowadays those simulations are quite accurate and are used in a whole host of applications. It may seem strange, I'll stop. It may seem strange to use a computer simulation to try and help design an experiment, but that is what some of the work we do at Los Alamos. Thank you.
We could take one more question in 30 seconds. So the question in 30 seconds for the answer.
George Erickson, Los Alamos. You had mentioned that you had put some zinc in there for post-shot analysis, I imagine. Was this looking for zinc-65 positron activity or what?
I believe so. Malcolm was doing that from INC11. The issue was post-shot analysis in terms of neutron counts were started immediately in this radiochemical type work. The conclusion from that portion of this work is not different at all from the main from the other conclusions. They're identical. Okay.
Repeating a remark I made earlier, you'll have another shot at the speakers in the discussion tonight. We must move along. We're behind schedule. I'd like to call for the next paper, Tests for Cold Fusion in the Palladium, Deuterium, and Titanium Deuterium systems at 350 megapascals and 195 to 300 kelvins. This is a group from ORNL, and I believe the paper's been given by Dr. Wazlowski, is that right?
Thank you. First, I'd like to mention some of the other efforts at Oak Ridge that are being presented at poster sessions throughout this meeting. Some very careful calorimetry and high efficiency neutron detection measurements by Don Hutchinson. Lauren Fuller is also doing electrochemical experiments similar to those that were talked about this morning by Chuck Scott. John Bullock is doing a careful study of the power production or heat production by various chemical and electric processes in electrochemical cells, and he's also looking at the physical characteristics of palladium metals. And Lewis Powell is talking about the thermodynamics, basically, and kinetics of palladium deuteride. The talk that I'll be giving is some work. We've now gone down to liquid nitrogen temperature by Jim Blanco, Mike Nady, and myself in the geochemistry group at Oak Ridge, and with the very able help of Francis Perret of the Engineering Physics Division, who has really made this a rather good neutron detection experiment. The rationale of our studies was to investigate the possibility that electrolysis is not required to induce cold fusion, and that perhaps charging of palladium by deuterium under high pressure would produce similar effects to those observed by Pons and Fleischmann and others. After we started our experiments, we became aware of the Frascati data using titanium deuteride, and so we've investigated that also. At least in the case of the palladium system, there are various sources of data, one of which is shown here, showing the hydrogen to palladium ratios attainable as a function of a logarithm of pressure in atmospheres. Our experiments are conducted up in this range here, and you can see that at around room temperature to dry ice temperature, ratios, at least for the hydrogen system, on the order of 0.75 to perhaps 0.95 can be obtained. We're not exactly sure what the equivalent system deuterium palladium looks like at these pressures. Perhaps they're somewhat lower than these ratios. And our simple goals for the experiment were to monitor the neutron counts and the temperature of the reacting material as a function of time, and also look for short-term and long-term effects due to pressure temperature changes and steady-state processes. This is the cell design. It's a 3/16 ID stainless steel pressure vessel, and the entire system is immersed in a water bath, which is controlled to 1/10 of a degree centigrade. In the bottom of the cell, there's a thermocouple, K-type thermocouple, and also a thermocouple in the top of the cell. This is the reference thermocouple. This is the sample thermocouple. Gas is introduced through a pressure fitting along the annular space around the reference thermocouple, and the way we introduce the gas is to pump up a gas intensifier, and then there's an air-actuated valve in this line here, which essentially within a few tenths of a second introduces the gas into the cell. We also have a vacuum line on this line here. These are two of our three VF3 neutron detectors. We had four into and out of the board here, but one of them shorted out, so we're down to three now. And the water acts as the moderator, and we're detecting the thermal neutrons. Some of the statistics on our neutron counting. This is the description of the detector. You can read for yourself. Efficiency was measured using a californium-252 source, 6.5%, thermal neutrons moderated by water. And our background, is, which is quite stable, is around 9 to 10 neutrons, counts per minute, giving an overall sensitivity, combining these two factors, of 140 neutrons per minute or 1,100 neutrons per hour. This sensitivity level is more than 1,000 times that of the Frascati experiment, and perhaps more than 1,000 times that of the Fleischmann and Pons experiment, and actually somewhat comparable to the Jones study. This is a pulse height analysis. The noise level, background noise in this region, our pulse due to thermal neutrons, and our bias was set at channel 58 here. So we had good separation between noise and signals. I'd like to talk about detector noise. I haven't heard anybody else mention that with regard to BF3 detectors. That may be a unique characteristic of our system, where we could produce extremely large signals at will if we did the wrong things. One of the first things we did was fill the entire bath with ice in order to calibrate our thermocouples. After about 12 hours, we began to get very large counts, and you could see from the oscilloscope output that this was simply noise, and we tracked that down to the moisture on the high voltage connectors on the detectors when we dried them out back to background. We also found that turning on the lights in the room where the cell is, they're sodium vapor lights. If you turned it on slowly, could get bursts up to 70,000 counts, and that could be done reproducibly. And finally, vibration, various sources of vibration affecting either the preamp or the detectors would produce counts which we could reproduce, not reproduce, but we could reproduce the events, and the counts were on the order of a few hundreds of counts. So this is something that needs to be taken into account in long-term experimental systems. The material that we used, 99.8 atom percent deuterium gas. Palladium was 99.97, analyzed by spark source emission. It's a 0.004 inch foil, about 0.1 millimeter. And for the other experiments, we used a titanium wire, 0.05 inches in diameter, which we cleaned and then broke up into about 1/8 inch to 1/16 inch lengths to load into the cells. Sample preparation, I neglected a step here for the palladium. We initially cleaned the foil with concentrated HCl plus nitric, rinsed that off, heated the palladium under vacuum, high vacuum, to about 600 degrees centigrade, exposed it to about 1/2 atmosphere of deuterium gas to remove any oxide coating, then heated again under high vacuum for about an hour, and then we stored and transferred the palladium material under high purity argon. For titanium, we did not take this step. We weren't sure what the Frascati people did with their material, but we suspected that it was not very sophisticated. We simply chemically polished the titanium, rinsed it, and dried and stored it under high purity argon. This is a description of the experiments completed to date. We started our first experiment 3 weeks ago. We're very much in progress, and this is very much a progress report at this point. Our first experiment was with 0.7 grams of palladium wrapped around the reference thermocouple, the sample thermocouple, that was brought from, by the way, megapascals can be simply multiplied by 10 to give you atmospheres approximately. We first took the palladium up to 380 megapascals, let that sit for 50 hours, and then pumped away the deuterium and let that experiment sit for another 70 hours. And I'll discuss the reason for these control experiments in a minute. We then did the same thing with no palladium in the system, simply pressurized with deuterium. In the next two experiments, we pressurized with hydrogen gas, high purity hydrogen gas rather than deuterium gas. We then did an experiment with 7 grams of palladium filling the entire pressure vessel. And I'll show you the sequence of events in detail in a few minutes. And then we now have in progress an experiment with 9 grams of titanium pressurized with deuterium. The reason for the control experiments was this was actually our first experiment here. Temperature of the of the sample and reference thermocouples plotted here as a function of time. We saw that the sample thermocouple reached a much higher temperature. This dashed line is the pressure pulse, and they're all normalized to 0, being the time that gas was introduced. You see that the sample thermocouple rose to a much higher temperature and then decayed rather slowly over a period of about 10 minutes to the temperature of the sample thermocouple and also of the water bath within 1/10 of a degree. We then tried the same experiment with deuterium, no palladium. Unfortunately, the pumping process is not entirely reproducible, particularly as the gas bottle becomes depleted. The intensifier takes more and more strokes to reach ultimate pressure, and that is the reason for these pulses in temperature. And you can't really see it on this scale, but there are actually changes in slope of the pressure versus time. And also the thermal signal gets spread out. But notably, the sample thermocouple again reached a much higher temperature than the control thermocouple, although the decay was much more rapid back to the bath temperature. Similarly, with the hydrogen experiments, they were both very similar. Most of this pulse is the heat of compression of the gas, perhaps with some additional heating due to the hydride or deuteride formation. In our experiment with 7 grams of deuterium, unfortunately we had a data gap right at the critical time, but I think you can see that there is perhaps a suggestion of a tail similar to the first palladium deuterium experiment. This sample was pumped away and repressurized at a later time, giving a more normal response. We suspect at this point that this tail is simply due to a somewhat more sluggish formation of the deuteride rather than the hydride. However, the whole thing is not extremely reproducible, and the biggest problem we had was that our heat loss is much greater than we expected, and so we were sampling at 6 seconds. The shapes of this pulse is very much dependent on that sampling rate. So we could not really get a reliable peak shape in order to do a heat loss calculation. Our future experiments will involve some insulating material to cut down on that heat loss, and also a faster sampling. However, this is the type of response that we got on a short-term, 10-minute basis, pressurizing. This is megapascals divided by 4. This is the neutron counts cumulative from our detector, and this is the sample and reference thermocouple. And I think one can see that this is essentially a straight line with perhaps a slope slightly decreasing over that 10-minute period, indicating on this time frame, this is a 1/10 of a minute sampling, no excess neutron production. On a much longer time frame, I show the results here of our 7 grams palladium run. This is the temperature pressure profile. We first pressurized the system, causing PV heating of the sample, which rapidly decayed. Pressure also decayed somewhat due to that initial heating and then cooling. Okay, sure, no problem. Well, okay, I'm not going to be able to go into the details of this profile. You can see that we changed pressure and temperature dynamically. We brought the temperature down to dry ice temperature. We brought it back to room temperature. We depressurized. We repressurized over a period of 90 hours. And this is a log of the counts per 5 minutes. We see nothing. We see a few points above the 3 sigma level, but for a Poisson distribution, one would expect 1% of the values to be more than 3 sigma, and this is 3 out of about 1,500 counts. If we look at that on an hourly basis, again, we see the same result. We see essentially no points in this. Am I live? Okay. We see no points except one at the very beginning, which approached the 3 sigma level. I'll skip this. Our similar experiment with titanium, we initially pressurized at our bath temperature, dropped to dry ice temperature, brought back up to room temperature, went down to about 500 atmospheres, and dropped the temperature down to liquid nitrogen temperature, allowed that to warm back up to room temperature, brought the temperature back down to liquid nitrogen, and then pumped the gas away, and you can't see that part. And this is about 10 hours here. The only thing that's different from the palladium run is a small cluster of counts per 5 minutes above our 3 sigma level. If we look at that blown up the last 30 hours of the experiment, we see that those points are actually associated with a rather broad increase in the average counts, and integrated over 1-hour periods. We do have a cluster of points here which approach the 3 sigma level, and this corresponds to the event of allowing the system to come back to room temperature after liquid nitrogen at about 500 atmospheres, and this is about 2 hours after it had approximately come back to the bath temperature. Now again, this is just barely at our 3 sigma level, and this is on the order of certainly less than 1,000 times the kind of signals seen by the Frascati group. We do not know whether this is an effect of neutron production in the sample or simply an unusual event in the background cosmic ray flux at this time. We haven't reproduced it, but the cell is still assembled, and we will do that as soon as I get back. And so our tentative conclusions based on our studies so far is that we've seen no detectable neutron flux above background over any of our sets of pressure, temperature, time conditions investigated in either system. Although we did not anticipate such a rapid heat loss from our cells, we could not detect a sustained thermal anomaly on the order of 0.2 of a degree centigrade. And we think that correlates to something like we could see a watt of excess thermal production. We didn't see it, but the error bar on that calculation is very poor at this time. We could not see a milliwatt. Thank you.
Thank you, Dr. Wessler. Are there any questions or comments?
I have something right here.
Steve Coonan from Caltech. I'm a little bit confused. Some of the neutron data you showed us looked to my untutored eye about as good, if not better, than some of the A&M data we saw this morning. Some of the Texas A&M data we saw this morning.
I think the
Why aren't you claiming an effect?
Well, because I'm sorry, are you referring to this last diagram here?
Yeah.
If we reproduce it several times, then perhaps we'll claim an effect. We have not done that. At this point, we can say that there is a variation on the order of 3 sigma for a period of about 5 hours. Now, one thing I'm glad you asked that, and somebody earlier asked about atmospheric pressure variations. This is a log of one of our earlier experiments as counts per 2 hours over a 5-day period. And you see a rather pronounced change in the background level over that period. We have found that if we look at this swale right here, although this is, you know, a few percent of the total background, if you look at the atmospheric pressure trace over that time period, it correlates rather nicely with that, with that jog. Yeah. Now, if there was an event, now we also have large accelerators and high flux reactors and all sorts of things like that at Oak Ridge. If something kicked on at that time, we could have gotten a 5-hour spike. We don't know that at this point. The event occurred at about 4 o'clock on a Saturday morning, a.m., and no one was there, so we don't think it's noise. in the detectors, mainly because our short-term counting doesn't show any unusual spikes. But we certainly couldn't say that that was a neutrons produced by the titanium deuterium system at this point.
Sensitive to environmental influences than are your counters particularly more sensitive to environmental influences than the scintillators that other people are using?
The only protection that we have is the high pressure hydrogen system, for safety reasons, was built inside an old cobalt-60 source room, which has 1 meter thick borated concrete walls, and it's in the basement of a building. Other than that, and by the way, when we roll the doors back, the door is on railroad tracks. When you roll the door back, you don't see any change in background. So I don't think there's any spectacular protection.
I have a question. Have you charged the battery temperature below?
I'm sorry?
Have you charged, pressurized the system, the battery temperature and below?
No.
Have you seen any difference?
The critical temperature for the system?
Yeah.
No.
Or when you're below, you have discontinuities. You can produce a lot of cracks below the critical temperature. You can they are discontinuous, and you produce a lot of cracks and lattice imperfection and everything. But you haven't done any experiments.
We haven't looked at the solids at all.
Yeah.
We have them, but we haven't looked at them. Yes, sir. Let this guy.
Scaramuzzi, Frascati. Just I missed the point. Last view graph, in which you showed the small effect, which was the pressure during those 5 hours?
That was, I'm sorry, that was approximately 600 atmospheres of deuterium in the system at that point.
I guess we could take one more question if it's a short one.
This guy right here's got it.
Turkovich, University of Chicago. I miss in this talk and in some of the others reference to the heats of formation of the hydrides, which I gather are not small.
Right.
As I understand it, the palladium is around 9 kilocalories per mole and the titanium is 35 kilocalories per mole. That's enough to heat the local palladium or titanium to very high temperatures at the time of formation.
Exactly.
Now, are these things reflected in either the calorimetric measurements or in your measurements? Are they seeable?
Well, we have a very high, as I said, we have a very high heat loss in our system. And our calculations, based on the kinetics data that we have available, suggests that the hydride formation at room temperature would be, well, that's not the right slide. Would be on the order of a few minutes, and that is exactly on top of our gas condensation heating effect. So we really can't resolve the two. But I think that with respect to the calorimetric studies, I haven't really seen too many people address that point, particularly if it takes many hours to charge the electrodes. I think that's a good point.
Is your question a short one? Short comment.
Okay, Birnbaum from the University of Illinois. The palladium hydride is in fact not a hydride, although it's often called that. It's a solid solution with a random distribution of hydrogen on the interstitial sites. If it were to order, and as you get the higher compositions, there is some indication, the phase diagram is not well known, there's some indication that there is an ordering of the hydrogen on those sites. You can have energy, enthalpy of ordering as high as about 50 kilocalories per mole, so that you can in fact get a very high thermal effect if in fact you get into a region where you're forming an ordered hydride, and you do in the titanium, of course, form an ordered hydride.
Thank you.
Thank you very much. Let's call now for the next speaker. This is measurements of heat, neutron, and gamma flux induced by MUSE stopped in deuterium saturated targets, a combined MIT BNL group, and I believe the speaker is Dr. Gaudreau, is that right?
Yes, yes. Okay. As you know, my name is Marcel Gaudreau from the Hot Plasma Fusion Center at MIT. I'd like to talk to you today about a facility and some experiments we've done at Brookhaven, where we've stopped some muons in deuterium-saturated targets. This is a collaborative effort between the MIT Plasma Fusion Center, the Physics Department, the Laboratory of Nuclear Science, the Chemistry Department, the Nuclear Reactor Laboratory, the Francis Bitter National Mang Laboratory, and also Brookhaven National Laboratory. I'd like to specifically acknowledge the invaluable help of Jim Riley, Jim Hurst, and Kelvin Lind of Brookhaven National Lab, and also the alternating gradient synchrotron operators for their around-the-clock help 7 days a week for this effort. First of all, I'd like to answer a little bit why this experiment. Well, first of all, it's been proven around the world in many laboratories for the last several decades that you can catalyze fusion in hydrogen isotope targets either at high pressure or in liquid state. The other thing is that the subject of this conference has been reported that you can have fusion in metal hydrides. And also the third item is that metal hydrides have similar hydrogen densities as these liquid or high pressure targets. So the question we're trying to answer is what would happen if you were to put a flux of muons into a metal hydride target, and specifically how many neutrons do you get for each muon stopped, and also what happens to the muons? Do they get captured quickly by the heavy Z nucleus, or are there lattice effects due to the shielding of the deuterium around the atom? For those not familiar with this kind of work, it's very different from tabletop electrochemical apparatus. That's a real understatement. It's even very large apparatus compared to the type of work that we do at the Fusion Center, where hot fusion. First of all, typically here at AGS, you start off with a bundle, 12 bundles of 10 to the 12 protons that you accelerate up in a ring. The ring is about a half a mile in circumference. Then it takes about a second. Then over a period of a second, you extract this beam and you take maybe 5% of this beam and you smash it into a 3-inch thick palladium target. This is why they call these atom smashers. You produces a tremendous amount of radiation particles, all of different kinds. The beam right here is within 10-foot thick concrete cave. After the platinum target, there is a whole scatter of particles of all different kinds, but some of them are pions that can be collected with some quadrupoles. These pions are momentum analyzed with a bending magnet. None of this is to scale, of course. Then the pions drift down a quadrupole drift tube where they can decay into muons. The pions that are continue through this magnet, smash into the wall. The pions, the muons that we're interested in are again momentum analyzed and are sent over to our target area. And then there's, of course, neutrinos that continue all the way through the wall and probably go all the way to Canada. Now, you, of course, can stand over here and right in front of this beam if you want. The neutrino beam doesn't hurt. Okay. On the other hand, the target area also has to be very carefully shielded. There's a very large background of neutrons and all kinds of other particles. So we had to add another 3 feet of concrete, steel, polyethylene, cadmium, and so on to reduce the background near our detector. This is an area where there really are a lot of neutrons, okay? We don't have to look for them. We just have to find the ones that we want. So we basically make a tomb for our detector area. Now this is a very simplified schematic of the apparatus. First of all, you have the collimated beam of muons that come through a lead collimator about 3 feet long, about a foot in size, with a 2-inch diameter hole down the middle of it. This muon beam that's been collimated then comes up into the detector area, where we then define a beam. Okay, there's still muons outside of it, but the beams can come through 3 scintillators right here, and we make sure that the beam, the muon, is actually seen at all 3 scintillators, but not seen on the other side of the target. This is the target right here. Some muons come in and are actually stopped right in the plastic scintillator. Some get stopped at the second scintillator, some in the air. Some of them actually go all the way through the target. A muon of this kind of energy, momentum 80 MeV over C, will go through things easily a 1/4 inch of lead. And in fact, we actually have to keep something like 1/8 of an inch of lead in front of here to degrade the beam so that actually the muon will be absorbed in the target. If we detect a muon, i.e. it's seen at all 3 detectors and not seen at the end, we electronically detect that signal and gate either the sodium iodide detectors, which see neutrons that come from the target, hit a hydrocarbon block inside here. Again, everything is very simplified here, and emit a gamma. The neutron can also go directly into the helium-3 counter. This helium-3 counter consists of 12 tubes, high-pressure helium-3 tubes, about 1 foot in length, 1 inch in diameter, that are cast in or mounted inside a solid block of polyethylene, about 1 foot in diameter, 1.5 feet long. So they're just pushed in here. The whole thing is wrapped in cadmium. Then that apparatus is put inside a 55-gallon barrel, which is then again wrapped with cadmium, and in between it's filled with polyethylene. The idea being is that slow neutrons come from the outside, they hit the cadmium on the outside, and they're immediately absorbed. Cadmium has a very high cross-section for slow neutrons. Then the fast ones can go through that, if there are some, of course, which there are, a lot of them. They get slowed down in the polyethylene beads, and then there's another layer of cadmium, and then hopefully they're stopped there. On the open end here, there's only cadmium because we're looking at the fast neutrons. The slow neutrons that are drifting inside the tomb will be absorbed by the cadmium and won't affect our measurement. If I can get the slide, first slide. Have a temporary difficulty of the apparatus, which is, we might need the lights down, I think. Can we turn the lights down? Can we turn the lights down? Well, I guess I don't know if we'll be able to see that there. Maybe we can go to the next one. This one isn't critical. Okay, well, this will give you an idea. Just to give you an idea what was on the other slide, I'll describe it to you. One of the smaller blocks of the apparatus is a solid block of steel 3 feet by 3 feet by 10 feet long that we put in between the quadrupole and the magnet. You can see part of it behind that lead piece there. Actually, the darker brown piece on the top is a solid block of steel, and this is a relatively small piece compared to the big pieces that are on the synchrotron itself. You can see the 55-gallon barrel drum there. I'd like to stress that all of this was put together relatively quickly, the last 3 weeks. We had another detector that we totally modified. So you can see on the outside the layer of cadmium. You can see on the inside the round circle there. That's the block of polyethylene, about 1 foot in diameter, with the little silver spots. That's the back of the helium detectors that are stuck inside. You can't see there, but there's actually a big hole that goes all the way through the detector in the center, and I'll talk about that a little bit later. You can see the blocks of lead there. You do a lot of moving around of lead when you work in high-energy physics. And you can see the beam there that's partially collimated. It's about a hole about this size. And on the right, you can see one of the sodium iodide detectors. This is at a very early stage I'm going to build upon here, which is banked on one side there. The next slide. Okay, here you can see a little bit more. You can see the helium-3 barrel on the right. You can see some of the helium, the scintillation collimator photomultiplier tubes tied on the monkey rack there. You can see the hydrocarbon blocks on the right over by the drop light there. This is again only once some of the apparatus is in place. Once you put all the scintillation counters in there and you've moved everything together there, you can't even see the target. It's very difficult to put your hands in there. Next slide. And here, this is not even at the end here, where you've kind of added more blocks into the tomb. When you're finished, the actual opening is just big enough to go in sideways, and you can see the thickness of the walls all the way around. Okay, I think that's the end of the slides. We've tried a number of target materials. Some of them have been pressure-formed hydrides, some of them electrolysis-formed hydrides, and of course, the famous control targets, the very necessary part here. The pressure-formed hydrides were done usually typically at about a couple hundred degrees C, a couple hundred PSI for something like 10 hours. We've done palladium deuteride with a D over PD of 0.7, which is typical. Vanadium deuteride with 2 deuteriums. We have done titanium deuteride and lanthanum trideuteride. These are all been solid targets except the titanium, which had to be done in powder form because of the diffusion time. It's much longer. The electrolysis formed hydrides we've done with 1 millimeter thick slides, plates, and palladium round rods, 6 millimeter in diameter. We've also used palladium targets that have been just swaged, and other ones that have been annealed at very high temperature, where we have crystals of the order of 1 or 2 millimeters in size, almost like cast. And we've of course done control targets with air, with heavy water, with palladium, with lead, and with deuterium gas in lecture bottle sizes. As far as results, I'll take the very cautious stand in saying that as far as excess heat, we certainly haven't burned our hands on any of the targets. Okay, I'll say I'm very cautious here because it's a difficult experiment to do. We didn't have much time, and we're working very hard on this. We've been very careful to calibrate all our detectors. The neutron source, we used a californium low-intensity source, and also americium beryllium source, a more intense source, so that we know that the place where we put the detector, where we put the target, our total efficiency is about 1.5%. And again, cautious that depends on how many layers of cadmium you put in, if you have a scintillation detector in between your target or not, or if you have moderator in front. There's many little things that go into here, but typically 1.5% is a good number. Now we're also upgrading our detector so that if you look at the detector here, as you saw in the view graphs earlier, the neutron detector is to the side of the target, so you only have a small solid angle. As recently as yesterday, we've actually taken this detector and actually moved it over here, so it's like this, and so that the beam actually goes, actually goes right down the center and put the target right in between the tubes. There's a little hole about this big down the middle, so that you actually have a 4 pi type of detector, and then the efficiency is about 15%. This is very high. I mean, if there's a few neutrons in there, we ought to see them. The key thing that we're trying to prove is what would be the upper limit on the number of neutrons per muon stopped. And we don't want to give a number right now, but we're working very hard on that. To end here, I'd like to say that we've formally asked the laboratories that have seen positive results if they could bring their targets and put it in our facility beam. We also would like to hear any suggestions, or even if you have a source you think that might do it, if it was in the beam, we'd be glad to try it for you. Thank you.
Are there any questions or comments for Dr. Gaudreau?
Okay, which one is it going to be?
It's not working. Okay, John Wacker from Pacific Northwest Laboratory. Two questions. One, are you set up to look at for muonic X-rays from this system? And second of all, are you going to run an actual electrochemical cell? I mean, can you do that inside your system?
Yes, yes. We both answers yes to those. We can put an electrolytic cell in there, and with the sodium iodide, we can look at the lines in there.
Also, are you looking at neutron multiplicities? In other words, are you sensitive to bursts of neutrons?
Probably. I'll take a very cautious stand here. If there is very large burst over time, there's no question we'd see it. But if two came very close, it's more difficult.
Moshe Guy, Yale University. When I first heard about your experiment, I tried to look at the number, and it seemed to me that most of the muon that you produce would be simply captured by the high Z material, by the palladium. Yes. And I'm not so sure. I mean, have you looked at the number? Are you going to see anything aside from just muon capture in palladium? And are you seeing the effect that you will see, such as neutron, X-ray, etc., from the simple capture of muon on palladium?
No. There's no question that that's the biggest problem with the experiment, but there are some theoretical explanation why the nucleus might be shielded by a lattice effect. There's a Livermore paper by Stan, do you know the name of it? Stan Lockhart right here, I think. Yeah, I don't know what the, Stan, you know the name. At any rate, it's a Lawrence Livermore paper that might explain one reason how it's possible. But that's a critical question to be answered. It's the most fundamental one, probably.
Chaplin, is that the paper?
Yeah. When Marcello Pavana from the Triumph Laboratory in Vancouver, we did this very same experiment as you guys did, although I don't think we did it nearly as good as you guys are going to do it. I was just wondering what it is that you're going to measure. I mean, you're going to measure the neutrons. You're going to measure the lifetimes of the neutrons, say, and also maybe the electrons coming off the capture?
Yeah, the quantity.
Just the quantity.
The quantity.
So you
we like to see the lifetime when they happen. We'd like to see the gamma rays that go with. We'd like to see all of that.
Because I didn't see a TDC on your diagram, so you are going to check for the lifetimes.
Yeah, we're checking all of those.
Oh, also, that paper is Gwynnon, Chaplin, and Moore from Lawrence Livermore.
Yeah, yeah, sounds right. There are copies around, and we can get you a copy if you want. Sir, Livermore would be glad to give it to you. Glad to.
Hi, John
If anybody
Marshall.
who has suggestions after the meeting, we'd like to talk. And Stan Lockhart here is also.
My name's John Marshall, Marshall Laboratories in Boulder, Colorado. Could you get interested perhaps in doing monocrystalline palladium? The reason is this. There's, in the most recent Scientific American, there's a very interesting article entitled Electron and Positron Channeling in Crystal Lattices. And what it says in this case is that muons might channel right down deuteron channels in a crystal lattice. So I'm hoping you might be interested in monocrystalline palladium.
Yes, if you had one of those, we'd be glad to put it in. One of the targets, as I said, one of the targets that we have is very large crystals. I mean, you put it in your hand like that and you can see them, you can count them. And this was done at very high temperature near the melting point for a long period of time. Like a few degrees, like tens of degrees below the melting point overnight will give you very big crystals.
Robert Eagleton from California State Polytechnic University in Pomona. I was wondering, what you're looking for are the neutrons produced in the fusion of two deuterons, is that right?
That's right.
Well, that would imply that there's two deuterons in an octahedral site when the muon is captured, right? Well, if the two deuterons are not in a common octahedral site, what's the probability that two deuterons can get together in a common octahedral site while the muon is captured?
I think I'm taking the purely experimental side here. Okay. I think maybe there are other gentlemen here that might...
Maybe I should save my question for him then.
Yes.
Okay. Is he going to be speaking next?
No, but there are plenty of people here that I'm sure would like to answer that.
Okay, I'll catch him later then.
Last question over here, please.
Eric Wheatley from JCOR. Could you comment on the spectrum of your muons and how they compare with the natural muon spectrum at the Earth's surface?
These are about 80 MeV per C. I don't know exactly what it is, but I know it's supposed to be typical of what you have on the Earth's level here. It's certainly much more intense. We're talking about 1,000 muons per second per centimeter squared, approximately. So it's many order of magnitude more than you would have in any environment, approximately.
Thank you very much.
You have a muon facility, so that's why.
Thank you. Let's proceed to the next talk, please. High precision cold fusion calorimetry achieved by in situ catalytic recombination of evolved gases. This is a team from the University of British Columbia, Vancouver, Canada, and I believe the speaker is Dr. Hayden, is that right? Thank you.
Hello, is this working? I'd like to start by thanking Reed Jensen first for letting me into the program at such a late time. And then I'd also like to thank, these are all the people I've worked with, but in particular I'd like to thank Uli Nardiger and Jim Booth for helping me work through the night on many, many occasions in the last few months. What I'm going to present is not so much of a not the results. We do have negative results. However, I want to present a technique which I think has a particular applicability to cold fusion electrolytic cells. Over the past few months, I'm sure everyone in here has run around and looked at cells like this, where you try to do some sort of calorimetry. This is similar to one of the first cells that we set up. You do a 4-wire measurement of the power input to the cell, which is sitting here with the electrodes in the standard sort of solution. You have a calorimeter which measures the absolute heat output of this cell. It's usually some sort of continuous flow calorimeter where you would measure a differential temperature increase from some cooling water. You also would, of course, make sure you monitor the temperature. And then you also have some technique where you measure the gas flow rate. And this is, in the case I've shown here, this is a measurement of the complete gas flow rate. This is everything which is coming off this cell. And then you write out some sort of balance equation. And you look for some sort of excess or deficit. You know the input power, and if you do your calorimetry right, you can get P thermal quite well. The problem lies in the vapor energy. You don't know how much energy is being carried away by recombination, by D2O vapor. Some of this vapor may recondense inside your calorimeter. Some of it may condense outside your calorimeter. There are a lot of problems associated with it. The most naive approach, of course, where most people probably started, you realize very quickly that you have to go further. You measure this flow rate, and you say that 2/3 of the gas coming off is D, 1/3 is due to the O2. And you can work out a number which tells you how much energy, the electrolysis energy that this represents. And finally, you can write out an expression for how much energy is carried away by this vapor. You realize right away, of course, that there are a lot of problems with this. The most notable problem is that you haven't included the finite vapor pressure of the D2O. So it's relatively easy to correct for that at first. You know the vapor pressure of D2O and H2O, which I might point out are different enough that if you're doing a comparative experiment between two cells, you do have to take the difference into account. And you find that at a moderately low temperature, like 20 degrees C, this pressure the pressure due to the vapor makes a 2% correction necessary. That correction rises quite high as you move to higher and higher temperatures. So again, you can write out an expression, and here you just account for the vapor pressure. However, at that point, you still have to think about the evaporation. You are evaporating D2O, especially at the higher temperatures, and that should be corrected for. So again, you know what the latent heat of vaporization is, and then you can repeat this. Again, for a saturated vapor, you can write out some expression, and here I give an example at 23 degrees C. This correction turns out to be 24% of the 2% correction you had to make due to the vapor. Well, if you're trying to do calorimetry down at this level, and you don't know if you have saturated vapor or completely unsaturated vapor, you've got to consider this thing. You just don't know where this energy is going, whether it's being deposited in your calorimeter, whether it's there in the first place. So this is what the problem we came up against. We got to this point about a week into the game and started thinking very seriously how we could go about trying to get around this problem. And we decided the only way to do this is a completely closed system in which all of the thermal processes occur inside your calorimeter, and you do a measurement of the absolute energy generated inside that. The design that we came up with back then looks something like this for the cell. And this is something that it's undergone a few modifications, and we've studied it in great detail over the past 6 weeks. What you have is a cell containing your electrolyte, usually the 0.1 molar LiOD and D2O. You have a cylindrical platinum anode, which is shown in black, and you have a cathode, which you hang down the center. These are just glass supports for the anode. The cathode sits underneath a funnel designed to collect the gas which comes out off the cathode, and the gases from the anode pass up into the space above the water level. At all times we monitor this pressure, but this is a sealed port. To start up the cell, we have a palladium wire, a fine wire, which we can pass a current through. We turn it on until the filament glows orange hot, and then we turn on the electrolysis current. We generate gases which pass up, and the D2 is funneled directly onto the palladium wire. The O2 is filling the space. The gases meet in this region and recombine, and we initially see this as a flickering in the intensity of the light. At that point, we turn down the filament current and turn it right off, and we can sustain this reaction for indefinite periods of time. We feel that we have essentially 100% efficiency in recombining the gases. At no time during the operation of this cell does the pressure fluctuate by more than, it's about a tenth of a torr. And these are fluctuations on small time scales. Long time scale fluctuations are under this level, and by that I mean the order of weeks. This cell is leak tight. No gas is escaping. So we turn this on, and we do several calibrations. First of all, inside this cell, I haven't pointed it out, but we do have a resistive heater. We do an absolute measurement with our calorimeter. The combination of the calorimeter and this cell give us a 0.3% accuracy in the absolute heat balance. We've also tested the calorimeter without this cell in it, and we've put in localized heating. I mean, in very temperatures over 100 degrees in all the corners and all throughout the cell. We're essentially completely insensitive to any gradients or any localized heating. The calorimeter is a continuous flow calorimeter. I won't go into much detail on it right now. We will publish this. But there's essentially a copper can here, which is somebody joining the conversation here, which is thermally linked to this cell with a very low vapor pressure oil. Let's see, the other things we do here. Okay, so we measure the temperature rise of this water, and this gives us our power, the thermal power generated by the cell. Now we do a final, well, I should point out that we have studied this calorimeter outside the cold fusion aspect of this thing quite a bit, and we do feel that we understand what's going on. We've done several things, like we know the thermal response times of this thing at various conditions and so on. What we do then is we do a calibration with 2 platinum electrodes. We turn the catalyst on and we run for very long periods of time, taking data continuously. And in order to summarize this calibration data, what I've done is to find a quantity which I call kappa. This is essentially the power going into the power measured coming out of the cell divided by the power input. There are factors such as the specific heat which are missing, but we do this at a constant temperature, and we do measure these quantities. It's just for the sake of demonstrating this that I write it in this way. Over a very wide range of power inputs to the cell, the heating up at this upper end can be quite extreme. We see that this thing is essentially independent of the operating conditions. At this point, we're ready to try to load the sample up, or load the cell up with palladium. In the meantime, while all this was going on, we had been studying the several palladium cells, and we've been running other calorimeters in parallel. We typically load our palladium to about between 0.8 and 0.9 D to PD ratio. This measurement is done by periodically taking the sample out, weighing it, putting it back in. And we find that we can, regardless of how we go about it, we get usually the very same thing. So if we're doing something that we're concerned about, we don't want to take it out of the charging cell, we would put it directly into our other cell. But we have studied this, and we feel that we typically run between 0.8 and 0.9. So we put our 1 palladium electrode into us. We ran for 12 days, and I summarized the data as another plot with, this is the kappa for the palladium, normalized this time to the kappa for the platinum. We find to 0.3% that these values agree. There's essentially no difference that we can observe. So I think at this point, I'd like to conclude this by pointing out not necessarily the cold fusion results. I'd like to point out the details of this cell, which I think have some distinct advantages over other types of calorimetry on electrolytic cells. First of all, we don't have to account for any of the recombination, the flow of any sort of vapor outside the cell. It's a completely closed system entirely within the calorimeter. We measure an absolute energy balance to an accuracy of at least 0.3%. We aren't sensitive to temperature gradients. And then when we do run with a palladium sample, we see no excess heat generation to the 0.3% level over the range of power inputs, 4 watts to 18 watts. And after seeing the results from Texas A&M this morning, I've written down what these results correspond to in terms of a current density and an excess power per gram of cathode material. So you can see at 40 milliamps per square centimeter, we see no excess heating to the 1 milliwatt per gram level. I think at this point, I'd like to, as in the last talk, put out a call or for people who have seen definite results but aren't sure of the calorimetry. We don't feel that we understand the surface science and all these other things that are going on well enough to, at this time, make a sample which reproduces what other people have seen. If you have a sample and are interested, we would be interested in considering putting it into our calorimeter and see if we could do anything with it.
Thank you very much, Dr. Hayden. I think we could have a small number of short questions. Could we have this one here first, please?
Hi, Srinivasan from Texas A&M University. I think you have a very nice calorimetric setup. One question which I would wish to raise is about the vaporization losses. Mm-hmm. Now, in our control experiments, that is like PD in LiOH or right. PT in LiOD, we did not observe any excess heat generation. We did not observe any vaporization losses because the heat input corresponded to the heat output.
And this is you're calculating I'm calculating these things using the saturated vapor pressures then?
No, it was simply the heat input was simply E minus 1.54 times I, and the power out is what we really measure in the calorimeter. And
I'm not sure I quite understand because we this was done in response to our first calorimeters, in which we definitely determined these quantities. We determined that this vaporization did play a role. It's on the level of say a fraction of a % correction. However, if you want to do calorimetry at this sort of level, you would have to take that into account. What sort of error bars did you have on your?
Well, I think our error bar is roughly within 0.1 to 1% with respect to
0.1 to 1%.
Yeah.
And you still?
No.
I can't explain it because we certainly feel that we
The only thing is this, that our electrodes are relatively small and our currents, total currents are fairly small.
Right. We at the upper end of the scale that I showed here, we would be running localized temperatures inside the cell could get as high as 50 degrees. Certainly these quantities would start playing a role at that
but we were at room temperature, 25.
Right. Well, the calorimeter itself is always at room temperature. This is only localized heating. But at no point do we deviate by more than about 30 millikelvin from our operating temperature on the water that we're using. Yeah.
Take this one over here, please.
Yes, Steve Baker from Stanford.
Yes.
Forgive me if I've misunderstood the exact nature of your experiment, but when one inserts hydrogen or deuterium into palladium, one expects to see an exothermic effect, as the previous questioner mentioned, of about 30 kilojoules per mole.
Right.
It wasn't obvious to me from the results you've shown how that is reflected in your data.
The results that I showed were for a palladium electrode which had already been preloaded. If we change the power level, we do observe a deficit, and we can observe the charging. We haven't tried it yet, but we believe that we can charge right from 0 time.
Yeah.
However, at that point, we would have to bleed out the excess oxygen, which we would then have to correct. We would have to make corrections. So our error bars would be larger during the charging phase.
Okay, thank you. That's fine.
Could you pass that back 2 rows, please?
Yeah. Nate Lewis, Caltech. I would just like to comment on a possible discrepancy between the vapor pressure result and the energy balance. Mm-hmm. In the open system, there will definitely be a balance between the cooling due to the vapor pressure correction and any heating that you might get due to excess recombination. And simply because you observe a power balance of what you expect does not prove necessarily that you had no recombination or you had no vapor loss, just that those two might have fortuitously balanced. Absolutely. So I think one would have to take that into account, and I would enthusiastically support your design of a calorimeter as the best way to go.
Nate Hoffman from ETech, Rocketdyne. With regard to using weight measurement as the amount of deuterium that goes in, I've examined specimens from all sorts of tests in the cold fusion, I have always seen growths on people's specimens, the growths being platinum, sometimes chromium and iron, sometimes products from the glass, sometimes the entire surface covered with growths that are very sharp pointed, which I'm sure would interfere with any weight measurement and might even interfere with current density or overvoltage considerations.
Right. We have not looked at these things, have not looked carefully at the surfaces. However, what we do when we're finished with an electrode is we vacuum degas it. These are, of course, vacuum degassed before we begin to work with them. We then repeat this process, and we find that in every case, we go back to exactly the same starting weight that when we remove this. So these would have to be things that would come off during the vacuum degassing phase. We see no sign of weight gain. And we've repeated these, we have one electrode which we've gone through this cycle 10 times with, and we still see no weight gain from the initial.
Okay, Tanihata from RIKEN. I have comment on measurement of your deuterium contents inside the palladium. You should be very careful by this weight measurement because if electrolysis is going on, lithium also deposit or diffuse.
The samples are washed off.
There. And we have done ion beam analysis of those, and a lot of lithium going into there. So
actually going into?
Really going into, we measure down to 2 microns or so, and it's going into the palladium.
One more in the back, please.
John Appleby, Texas A&M.
Yes.
I'd like to make a comment concerning the evaporation of the electrolyte, which I should have made this morning. What happens is that the zero for our blank experiments, that is to say, platinum in D2O or palladium in H2O, lies about 1 or 2 millivolts negative of the zero. That is the evaporation.
Yes, I was thinking about that earlier.
That corresponds to about 1 or 2 milliwatts in our cell.
1 or 2 milliwatts?
Yeah.
Okay.
We'll take one more on each side. Over here, please.
Yes, I'm Lauren Fuller from the Oak Ridge National Laboratory. 2 questions very quickly. How much power are you dissipating to keep this catalyst in an activated state?
We dissipate whatever the gas flow is. It's the
but you said you had to put some IR heating in there to keep it active, did you not?
Sorry, I couldn't hear that.
Did you not have to keep some IR heat going in there to keep it active?
We have to supply a threshold current in order to get this to run. We find that for the particular wires we're using, we need to supply at least 40 milliamps of electrolysis current, which is very small, in order to have a self-sustaining reaction. We don't know the upper limit. We've only run it up to 2.2 amps of electrolysis current.
And this is just a palladium coil that you have up in there?
It's just a palladium coil, which self-heats.
Thank you.
Alan Bard, University of Texas. As long as we're talking about chemistry, let me point out we also find lithium diffusing into the palladium by a couple of methods. We also find silica sometimes depositing. The very alkaline electrolyte attacks the glass cells. Right. And it might be well, in fact, to start looking at alternative cells like Teflon other than glass because of the attack. Finally, let me point out one very old chemistry fact that probably only those of us who used gas coulometers 30 years ago ever knew, and that is that it's pretty well known. It's, for example, in Lingane's book that in basic solution, electrolysis of water is not 100% efficient to H2 and O2. There were always errors of 2 or 3%. Right. That was ascribed to peroxide formation at the anodes. So in the recombination cell, of course, that's not a problem, and I completely agree with you. The recombination cell is the way to go. But it certainly is a problem in the open cells.
Well, with regret, we'll have to truncate this discussion, and let's try to resume at 4:10. I'm assuming that that the 4th paper will probably not be given after the break. Thank you. Those who wish to discuss, please move the discussion outside. We have your attention, please. We'd like to get this session started. We're moving to a short session on the physics of fusion reactions. We have 3 presentations before we will return to the El Dorado Hotel, and there'll be directions about that later. But the first of these is entitled Nuclear Reactions and Screened Coulomb Fusion Rates, presented by Hale, Smith, and Talley from Los Alamos, and I believe Dr. Hale is going to present it.
I'd like to talk about some work that Rick Smith and Thurman Talley and I have been doing, some of it very recently, and it's, you know how that goes. And it's based on some work that Don Dotter and I have been doing literally for years on the thermonuclear reactions. I'm going to talk, and I apologize that it'll be a brief discussion for those of you who are not familiar with it, about the R-matrix approach to describing nuclear reactions. Turns out to be a very convenient way to describe a system, many-body system of interacting particles that have both long-range and short-range forces, which we certainly have in this case. And then, based on these results and the results of others, I'll also talk about properties of some of the low-energy reactions that have been proposed as possibly explaining what's going on in the cold fusion experiments. And finally, I'll talk about a way to calculate reaction rates for complex systems, which are the kind of systems we're talking about. Actually, the idealizations that I'll discuss will be very simple versions of those complex systems. And in particular, I'll talk about an analytic example in the case of a screened Coulomb potential for which you can solve the problem without having to resort to a numerical solution. And finally, of course, I'll make some conclusions. First thing I show here is a description of how one calculates reaction cross-sections using this R-matrix approach. The central quantity that I'll be discussing is this R with a superscript L. And this, for those of you who are familiar with scattering theory, is a projection of the outgoing wave Green's function for the short-range interactions of the system onto a surface which is called the channel surface or the nuclear surface for the reaction. And I won't be able to go into much detail about that, but you can tell from the terminology that it suggests that we're projecting things on the region where the short-range forces are acting, and that the long-range parts of the interaction will be put in at some later point. Actually, this quantity, R sub L, is a composite of the two effects, but it's mainly a quantity that's sensitive to the short-range effects. And in these
expressions or define some of the quantities below. This channel label contains a lot of quantum numbers, but it also suggests this projection I was talking about on the channel surface or on the nuclear surface. And then these quantities P are simply penetrabilities, and in the nuclear reaction case, these are penetrability, Coulomb and angular momentum penetrability quantities that are expressed in terms of the wave number for the reaction. The AC is the channel radius for that particular alternative of the nuclear reaction. And then this O is the outgoing wave solution in the long-range potential. And typically what we deal with is the situation where these are Coulomb functions, but they don't have to be. They can be the outgoing wave solution in any long-range potential that we want to discuss. And this is the RL quantity that, as I mentioned earlier, is the projection on the outgoing wave of the outgoing wave Green's function on the channel surface. And it's written down here in terms of the parameters that we actually use to describe the experimental data. The gamma C lambdas and the E lambdas, which are the eigenvalues, and the reduced width amplitudes of the R matrix parameterization. This logarithmic derivative, which I've called capital L, is simply the logarithmic derivative of the outgoing wave solution. Now, in terms of all those quantities, you can write down this expression for the reaction cross-section for some initial state going to a final state. And I have in mind, of course, a reaction like DD going to PT or DD going to N helium-3, or even DT going to N alpha, any of those possibilities. And what I wanted to show in the bottom part of the slide is that this expression does indeed reduce to the kind of expression that people are used to seeing for low energy cross sections. The penetrability in the entrance channel, of course, goes in the low energy limit to the gamma factor, and the k squared that comes into the cross section expression, of course, becomes a 1 over E essentially. And then everything that's left over, this rather complicated expression, can be lumped into what's called the astrophysical S function, which is in general somewhat energy dependent, but most people don't worry about that and just evaluate it as at zero energy. So using this sort of information and the information that other people have obtained from looking at some of these reactions, I wanted to make a summary of the properties of the reactions among the hydrogen isotopes that fuse. And I'll just sort of go up in mass number, and some of these I won't say much about beyond what's on this slide and the next one. One of the reactions that's been talked about a lot is the PD gamma reaction. And you can see that based on the work that's been done, we have not incidentally done an R matrix analysis for this reaction yet. But based on the information that exists for the astrophysical S function, it appears that it's about a 50-50 mixture of S waves and P waves at very low energies. And then the P waves become increasingly more important as you go to higher energies. For the A=4 reactions, these two I've lumped together because they are very similar on the basis of charge symmetry. They are also a mixture of S wave and P wave at low energies. Even if you go to the lowest energies, they still have about a 14% P wave component to the cross section. And one thing I'll be talking about in a little bit more detail later is the branching ratio between these two branches, because that's been of considerable interest. There's been speculation that perhaps the proton branch is very strongly enhanced at low energies by something like the Oppenheimer-Phillips effect. And we don't find that such a thing is really possible. The DD gamma helium-4, of course, has been the subject of a lot of discussion, not so much in this form, but in the equivalent form that might be going on in the lattice. And I've summarized some statements from a very recent paper that I just received from Duke about this reaction. Usually the statement that you hear is that this reaction is occurring out of incident D waves through an E2 electromagnetic transition. And that's true at higher energies, but at very low energies, which is where we're interested in it, it appears that a large part of it is coming out of the quintet S2 state. And again, there is considerable contribution from the P waves in this reaction also. The DT reaction is the only one that is really very simple from a nuclear physics standpoint. It's almost completely S wave, and it's almost completely dominated by the famous 3/2+ resonance that many people know about in that reaction. But as I say, before I leave this, I want to emphasize that's the only one that's simple, and the others are in general mixtures of S waves and P waves, so we won't necessarily get away with the assumption of treating everything as S wave just because it occurs at a low energy. I want to summarize also the numbers that we actually calculate for the S function and this reaction constant A0. I'm having trouble getting things to stay here. Anyway, the S function that I mentioned before and the reaction constant are related just by other physical constants, and so I put in the numerical value in this system of units for those constants, and I've listed those values here for the reactions that we mentioned earlier. And these values in this column are the ones that we calculate from our matrix analyses, and then we extract these values for the reaction constant. You can see they're not really much different from the numbers that have been floating around in the literature for a long time, originally coming from Fowler and company, and more recently Steve Koonin has calculated the A0 values that go along with some of these. And I've arranged these in the order of decreasing S function or reaction constant. But by now, and this will be apparent in some of the things that I'll show later, it's well understood that there is in fact an inversion in order of these, the ranking, if you will, of these cross sections, the magnitudes, as you go to lower and lower energies because of the famous dependence in the penetrability, which also comes into, in addition to these factors in the expression for the cross sections of the rates, in the gamma off factor that comes from the differences in the reduced mass dependence in the gamma off factor. This is not true, incidentally, though, for the DD gamma. It still maintains its roughly 10 to the 8th or so difference below the DD reactions, even taking into account those reduced mass factors. One of the things that I meant to point out on this, though, is that one of the slight differences that we have from our results and the earlier ones is that there is a difference in the S function and the reaction constant for the two branches of the DD reaction. They're not much different, but the proton branch is in fact slightly enhanced over the neutron branch. And I'll show you some data along with our calculated curve. These are some of the most recent measurements. One measurement that was just finished up this year at Los Alamos, and then an earlier measurement that was done in Germany. And you can see that although the error bars are rather large and there is some scatter, that the trend of the data certainly suggests the sort of behavior that we have for our curve in this region where the measurements have been made. And then our extrapolation is almost asymptotically approaching a value for this ratio of about 1.04 as you go to very low energies. Now, there's been some speculation that maybe the Oppenheimer-Phillips effect, which you may remember would presumably allow the neutron to tunnel through the barrier without being impeded by the Coulomb, and therefore enhance the PT branch greatly over the N-helium-3 branch. It has been proposed as a reason to perhaps get radiationless, or not radiationless, but neutron-free fusion out of the DD reactions. But it turns out that the Oppenheimer-Phillips effect, because of the symmetrization of the nucleons in the two deuterons, cancels to first order in the deuteron polarizability. And furthermore, if the effect is not evident in data down to these energies, it's very unlikely that it would all of a sudden start coming in at very low energies, because that would correspond to the overlap of the deuterons far out on the tails of their bound state wave functions. So we feel that our prediction is probably pretty good for that. That ratio I just showed is for all the partial waves, but one interesting thing is that the ratio is quite dependent on which partial wave you're talking about. That ratio, of course, is dominated mostly by S waves, but in the P waves, when we pick out just that part of the cross-section, we calculate a ratio, and now I have to confuse you a little bit by telling you this ratio is really the reciprocal of the other one I just showed you. This is the N-helium-3 branch divided by the PT branch. That turns out to be surprisingly large, something like 1.4 for reactions that are presumably charge symmetric. And this is a pure prediction. We had no data telling us about this, but then later I found out there had been some measurements done in the Soviet Union, and they, with mu-catalyzed DD fusion for one thing, and some polarization measurements, and they measured almost exactly the same ratio. So again, these things are quite dependent on which partial waves you're talking about, and makes it important to take into account the partial wave behavior of the reaction. I want to switch gears just a little bit and talk about how we would calculate rates in a composite system, because so far what I've been showing you are data for the nuclear reaction case where asymptotically you know that the wave functions are Coulomb waves, just pure Coulomb repulsion waves. But of course in the case that we want to discuss, we know that there's some sort of long-range potential out here that is screened most probably with respect to a pure Coulomb potential, and one of the problems is we don't know exactly what it looks like, or at least I don't know exactly what it looks like. It might have a well, it might just be screened a little bit. So this is one thing that needs to be known, but my point is that whatever that...
Just try to wind it up in about a minute or so.
Okay. Whatever this is, it should be possible either analytically or numerically to calculate the outgoing wave solutions in that potential, and to use those in just the same way that we normally use the Coulomb potentials in these calculations. And the thing that's interesting is that the R matrix quantity, this R matrix amplitude, is also going to be a little different in that case, because this logarithmic derivative of the outgoing wave solution will change a little bit. So if we know this potential, and if we also know the energy distribution of the interacting particles, we can calculate this rate. This rho of E, of course, is a familiar thing for a plasma physicist, because this is just taken to be a Maxwellian velocity, but again, in this case, a Maxwellian velocity distribution. But again, in this case, we don't know exactly what it is. So we've done some calculations using a very simple analytic form of the potential. And let me just briefly mention the results here. This is a rather complicated thing to go through, and I won't have time to do it. But I was just trying to see if, in the case of a sharp energy distribution, that this expression that I wrote down, the more general expression, reduces to the sort of expression that people normally use, namely this reaction constant times the outgoing wave, or the solution in the long-range potential evaluated at 0. And to make a long story short, we find that in at least the case that we've looked at so far, this approximation is not a bad approximation, and it depends on some conditions that I've listed at the bottom of the slide as to whether that approximation will hold or not. So let me finally show you some results for the simple form of the screen potential that we've chosen, the Hulton potential, which looks like a Coulomb potential at small distances and an exponentially decaying potential at large distances. So you can put in a screening radius, and that's what I've called this AS. And it is one for which analytic solutions exist, and so we can write down this quantity 1 over the outgoing wave squared. This is, of course, 1 over the Yost function. And we see that in the limit of large screening radius, this does go over to the Coulomb form that we would expect. And now let me show you some rates quickly with this calculation. The quantity that's plotted along the bottom is the screening radius in angstroms, and then at various energies we've done the calculations of the rates for the 3 different reactions that are listed here. And you can see that until you get up to fairly high energies, the screening radius does indeed have a significant effect of raising the calculated rate. The sort of rates that we were using as a benchmark were something like 10 to the minus 24, which is the sort of rate that's seen in the Brigham Young experiment and some of the others. And you see that that requires a rather small screening radius to get that kind of rate, at least down at these energies. Here's a plot at a fixed screening radius, but as a function of energy. And you see that, that this crossover begins to occur up at higher energies where the DT becomes larger, and these things are crossing over. This is what makes knowing the distribution of the energy for the interacting ions very important to know, because these rates are crossing over each other. And to even know what reaction is the most important would require knowing what that distribution was. I've got a couple of others to show, but I think since I'm running out of time, I better skip to the conclusions and say that in our calculations, we don't find any significant differences between the proton and neutron branch of the DD reactions at low energies. I thought I would just mention something that has been of interest, and that is the direct coupling of the DD, what would be the DD gamma in free space, to the electrons. This has to happen on a very short time scale in order to be competitive with the particle reactions, because they're going in times like 10 to the minus 21 seconds. And it's hard to imagine how, even at the speed of light, an interaction could travel out to lattice sites in that short a time. So we don't think that is a very good possibility. The PD gamma, on the other hand, or the PD coupling, might not be so restricted. And then, as I mentioned, for this simple Hulton form, we find that the approximate rate expression gives very reasonable answers. We're not so sure that would be the case if we looked at a well like the Morse potential, and so that is one thing we want to look at, and we're currently working on that. It looks like that to get the amount of screening that you need to get a rate like 10 to the minus 24 would correspond to reasonably high electron densities. And so we have the feeling, looking at these graphs that we've produced, that maybe a better place to look rather than screening is to think of processes that might produce higher energy interacting ions. And finally, along those same lines, the point that I just made is that these energy distributions are very important for calculating realistic values of the rate. The one I used in all the calculations I showed you was just a delta function, and we know that's not realistic. So if anybody has an idea of what these distributions are, I would certainly appreciate hearing about it. Thank you.
I guess we could have a couple of quick questions. We're well over time, but let's try one here first.
Tajima from University of Texas. Your potential, you showed the Bayer Coulomb versus some attractive potential. In fact, we can show that there can be attractive potential if the electron correlation and the deuterium correlation in the palladium is strong enough. And we, in fact, carry out such calculation. And of course, attractive potential can allow the deuterons to approach to a fairly short distance, even at room temperature. And we have a poster today up there.
Okay, I'd like to see that. Thank you.
Danos, NBS. These calculations have been done by ignoring actually the presence of the lattice. If one takes into account the possibility of momentum energy exchange with the lattice nuclei, one can find a change in the rates by factors 10 to the 20, 10 to the 30. I just have no time to explain it more than this.
Robert Perry, Ohio State. Sorry, I don't have a comment. But you showed the fusion rate dependence on this screening length. Could you make a comment about how reasonable or unreasonable the screening length has to be to get fusion rates consistent with the Jones et al. Results?
Yeah, it appears to be about 10 times smaller than the rate that you would, or the screening length that you would expect based on the expected electron density. Now that's a little bit misleading because I know that people have talked about average separations between the deuterons of much bigger than 0.04 angstroms is the number I'm talking about specifically. But of course these are done usually in a well too, and we're doing it in a different kind of potential. But in this case, that sort of screening length corresponds more to the distance of closest approach, whereas in the other cases it's sort of the average interparticle separation in the well. We do want to do a well, definitely, to see how this changes. I suspect our results might be quite different in a well-type potential.
No, I'm really sorry. I think we're really well over time. Could I ask you please to address further questions directly to Dr. Gale? Thank you very much. I'd like to call for the next paper, Molecular Dynamics Simulation of PD 1.1, How Close Can Deuterons Get, by Dr. Richards of Sandia National Lab.
Thank you. It's Peter Richards. Well, certainly a major question in all of this, at least if one thinks that bulk hydrides have anything to do with this, is how close can deuterons get? My approach to this has been to do a molecular dynamics simulation of palladium deuteride above stoichiometry, because there are reasons to believe, as I will go into, and you've probably heard already, that if you go above stoichiometry, there's probably a better chance of crowding things in together. I might also point out that the previous speaker mentioned that it would be nice to have distribution of energies of the interacting ions. Now, this is something that a molecular dynamic simulation can do. Unfortunately, I did not do this. I'm going to be talking about distribution of distances only. Now, so as to avoid keeping you in suspense, basically, you don't get very close distances in this, as I think people that are familiar with hydrogen and metals are well aware. Namely, you don't get anything closer than a D2 molecule. Also, during the course of these runs, typically a run takes about 10 hours. No excess heat was really seen in my computer. I find it somewhat surprising that until now, I don't believe anyone has actually shown a picture of the hydrogen palladium lattice, so let me give it to you here. The normal situation for below stoichiometry x less than 1 is that hydrogen occupies the octahedral sites, and the neighbor distance between octahedral sites is 2.83 angstroms, considerably larger than in the molecule. So you don't really expect maybe terribly interesting things to happen below stoichiometry. But if you do go above x greater than 1, then you have the possibility of getting things closer. One's first inclination, and I think it turns out to be right, is that the tetrahedral interstitial sites then become occupied. In that case, the distance shrinks considerably to about 1.73 angstroms, but of course still considerably larger than in a molecule. Now, one also wants to investigate the possibility that you might have multiple site occupancy in this octahedral site, and a related question that the molecular dynamics can answer rather nicely is, if you thermally agitate the system, will you be able to induce close approaches? Now, I'm making the assumption that not all of you are terribly familiar with molecular dynamics simulations. So let me go into what one does a little bit. Molecular dynamics does not necessarily mean the dynamics of molecules. It has come to be a generic expression for simply integrating the classical equations of motion, and the main thing that one has to put into here is, what do you choose for the potential in this n particle system, n in my case being 219. In general, this can be a many body potential, but in practice, we just work with two-body potentials. I'll go into the choice of the potential in a minute. One studies statistical properties as a function of temperature, and temperature in the molecular dynamics simulation is defined in terms of the kinetic energy. So that by choosing a distribution of velocities, one fixes the temperature and one can hold the temperature constant by readjusting the distribution of velocities as necessary. The second point concerns the time scales that one can deal with. If you have a dedicated cray, something like that, then one can work in the nanosecond regime. For the kind of workstation that I have, only times the order of 10 to the minus 10 seconds real time are practical. That means you can't study very slow diffusion, but on the other hand, this 10 to the minus 10 seconds corresponds to over 1,000 vibrational periods, so that one certainly can get interesting information. You can see how the system comes into equilibrium and study diffusion at relatively high temperatures. Now, let me discuss how one chooses the potential and the approach that I've taken. First of all, I should say that my object here has been to see under what I would call the most optimistic and yet reasonable conditions how close I can get the deuterons to come, and therefore I was not so interested in giving a detailed model of this PD D 1.1 system as just to playing around with different potentials to see within the bounds of reasons how close the deuterons might get. Now, there are three potentials in the system. The palladium-palladium is the simplest one to deal with and probably the least important, and what one does is to choose simple analytic forms, something like Leonard-Jones potential, to give you the proper lattice constant spacing between the palladiums and to get the right elastic constants. There. Now, for the palladium deuteron potential, the most important things, at least for these studies, are generally felt to be, first of all, the curvature at the bottom of the potential. That tells you the vibrational frequency of the deuteron in its interstitial site, so one tries to fix that. And the second thing that one tries to get a handle on is the activation energy for diffusion. So those are two parameters that more or less fix this palladium deuteron potential. Now, the most crucial thing for close approach of the deuterons clearly is this repulsion between the deuterons. And here I simply use a screened Coulomb potential and play around with this inverse screening length alpha, as I will discuss. Now, one can always criticize molecular dynamics calculations of hydrogen in metals because, as I pointed out, these are strictly classical. There are no quantum effects. But on the other hand, there has been previous work of molecular dynamics on palladium hydride that have been very successful in describing diffusion and inelastic scattering of neutrons. However, I should point out that these previous simulations all have been done at very low hydrogen concentration, and so questions regarding the hydrogen-hydrogen interactions really have not come up in the previous molecular dynamics simulations. Now, going on with this palladium deuteron potential first, I think it is more instructive, rather than to plot the potential as a function of distance, to plot it as you go along a path from the octahedral to the tetrahedral site along the 111, which is supposedly a minimum direction. And I show here two possibilities, more or less giving you the same activation energy for diffusion. The first where the tetrahedral site is unstable, and the second where it is stable. The dashed line is what was used in a previous molecular dynamics simulation where the tetrahedral site was marginally stable, so that by bracketing between these two, one should come up with something fairly reasonable. So I've considered both of these types of potentials. Now, a major question is, will the preferred energy, when you have above stoichiometry, be for multiple occupation of the octahedral site, or simply for having one in the octahedral site and one in the tetrahedral site? And so what I have done, and we'll show you on the next view graph, is to look at the energy along the 111 direction as one separates the deuterons from the central octahedral site position, and to compare that energy with one being at the octahedral site and the other being at the tetrahedral site. And this is the result. I might point out that this is very similar to a curve that is shown in a poster by Wei and Zanger, namely that depending upon the screening length, one can get various conditions for the energy as a function of distance as you go along this 1-1-1 direction. Now this dashed line is the energy of one in the octahedral site and one in the tetrahedral site, and only if you fall below this will double occupancy of the octahedral site be favored. And that occurs only if you go to a very, very short screening length, namely something like 1/4 of a Bohr radius. The value that I have chosen to use, and which is very close to, I believe, to what Wei and Zanger has, is about 1/2 a Bohr radius screening length. In that case, the multiple occupancy is metastable, namely you do have a stable light energy here, but it lies well above the energy if you had one in an octahedral site and another in a tetrahedral site. If you go to a screening length of 1 Bohr radius, then there's no kind of a minimum at all. The deuterons simply want to get as far apart as possible. I have then performed simulations under the conditions that I discussed. 2 temperatures were looked at, 300 degrees K and 1300 degrees K, for rather obvious reasons. 300 degrees K is what most people work at. The motivation for doing 1300 degrees K is to see if one has a large amount of thermal agitation in the system, that this will somehow or other produce events of close approach. As I mentioned, I used a palladium deuteron potential where both the tetrahedral site being stable and unstable were considered. Typically what one does is to let the system run for real time of 10 to the minus 11 seconds, which in computer time is about 10 hours. Let it quiet down, come into equilibrium. Then for another 10 to the minus 11 seconds, look at snapshots of the distribution of distances. And I should point out that these simulations were done for 108 palladium atoms and 119 deuterons. And here are the results. First for 300 degrees K, this is a plot then of the distribution of DD separations as a function of distance. And what you see in this case are peaks more or less at the octahedral distance and the octahedral tetrahedral distance. Note that this is a log scale here, so that one is considerably down in magnitude by the time you're at 9/10 of an angstrom. No distances shorter, in this case, than 9/10 of an angstrom were seen. Now, this is a relatively small sample, so what that really means is that any distances shorter than 9/10 of an angstroms occur with a frequency of something less than 1 part in 10 to the 5th. Now, if one goes to higher temperatures, then you do get closer approaches, as one might expect. In this case, for 1300 K, one sees distances down to about 7/10 of an angstrom. These are in 1/10 angstrom bins. So this corresponds roughly, for some small fraction of the time, getting as close as you find them in a D2 molecule, but certainly no closer. Okay. Now, the fact that one does seize a fair amount of distances in the neighborhood of 1 to 1.5 angstroms is perhaps of interest, and this is quite a bit closer than equilibrium distances. Now, in conclusion then, I have been given permission from Professor Jaina to quote from an article that was recently submitted by him and his colleagues to Solid-State Communications on a palladium-6 D2 cluster, which I neglected to mention on a previous slide. And I think this is a rather succinct statement. Namely, they're just, at least in the bulk of a hydride, as far as any of us that work in this field can see any reason why you should get distances closer than you have in the D2 molecule. In fact, they're considerably longer. However, if one is interested in perhaps less exciting things like NMR and neutron scattering, then I believe there possibly are some rather interesting implications of the fact that one can get a fair amount of short distances occurring due to this agitation. And finally, I do have to introduce the caveats, namely that these are strictly classical dynamics calculations. Any exotic quantum effects that are occurring will not show up here, and these are done with periodic boundary conditions, so it's strictly characteristic of a bulk Any exotic surface effects also are not going to show up here. Thank you.
I've seen literature that well under PD-D, around 0.8, let's say PD-D 0.8, you never fill all the octahedral sites, that no tetrahedral site is filled, and you have a tendency to get pairs on the 420 planes, even above the cryogenic ordering thing. Is the work that you're doing superseding these kind of articles, which were mainly neutron diffraction?
I think the ordering that you're talking about, isn't the ordering still within octahedral sites?
Yes, in octahedral, but on the 420 planes that cut the octahedral site, with a lot of them being empty.
Right, this is not addressing. See, I am creating, in a sense, a fictitious system, although it is not totally fictitious, because you'll hear a talk